In the earlier lecture, we saw the numerical solution of system of linear equations, which are the matrix problem, whatever we solved using numerical methods like we solved up to LU decomposition, single value decomposition, all those we saw in the earlier lecture. So in this series of lecture, we will see the another important matrix problem which we often encounter in while we are pursuing the problems in physics, and that problem is the eigenvalue problem. What eigenvalue problem? Where you have faced this eigenvalue problem, one of the very common area where you face this eigenvalue problem is in quantum mechanics, where you have, so if psi is a wave function, so to find the energy of the wave function, you operate with the Hamiltonian and then you get E of psi. Okay, so this is an operator. So operator will be usually a matrix. So in a matrix notation, so this will be a matrix and multiplied by, this is a state is a vector, so that will be a column matrix. So I can write it as say something like X, and energy I can call this as some energy level corresponding to that state X. So this is what typically we call as an eigenvalue problem. Okay, in an eigenvalue problem, in general, we have a matrix A, and when I'm multiplying the matrix A with a vector X, we will get a some lambda, some constant lambda in the X vector. Okay, and this lambda is called as your eigenvalue, and the X, the vector, when you operate it on A, which gives you the eigenvalue lambda, you call as your eigenvector. Okay, so now often this is a very important problem. Given an operator or a matrix A, you have to find out what are the eigenvectors and the eigenvalues corresponding to those eigenvectors, or conversely eigenvalues and the corresponding eigenvectors we have to find out. This is one of the very common problem we often encounter in physics. So in this series of lectures, we will try to see how we are going to solve this problem. Okay, so and if you see this equation, so what we can write, so I can slightly rearrange this equation as A dot X. I will take this one here, so it become minus lambda of X is equal to 0. This will be a 0 vector. Okay, so then I can take this X commonly outside. What are we going to get is A matrix minus lambda into identity matrix dot X vector equal to 0 vector. So this is something like B matrix. This is a matrix. B matrix dot X is equal to 0. Now we have seen the same problem in our earlier lecture when we were discussing about the singular value decomposition and all. So this matrix equation, which basically connects your, which basically maps a certain X into 0, that's what we call as a null space. So for this to happen, we know the B should be singular. Why? If B is non-singular, then we can write this equation as, if B is non-singular, then the inverse of B exists. B inverse exists. So then X vector is equal to B inverse dot 0. So that will be 0. That's a trivial solution. Okay. So if you want a non-trivial solution, then if B is singular, then the B inverse do not exist. Then there can be a vector space X, means finite vector space, non-zero vector space X, which can be mapped to 0, and that space we call as your null space that we saw in our earlier lecture on singular value decomposition. So for this condition to be satisfied, so B dot X to be equal to 0, and for a non-trivial solution of X, the requirement is B should be singular. For B to be singular, what we have is the determinant of B should be equal to 0. Okay, so then only we call B is singular. So similarly here what happened? So B is equal to what? A minus lambda I bar. So we have determinant of vector A minus lambda I equal to 0. So this is what, and if you see this, this equation, when you write this as A minus lambda I equal to 0, this is now when you try to solve it, what you will see is this will be a, suppose if a matrix A is n cross n matrix, if it is n cross n matrix, so what this equation is going to give you is a polynomial or nth degree polynomial in lambda. Okay, so therefore, so this equation is going to be an nth degree polynomial in lambda. Therefore, there can be n roots for lambda. So n roots means so lambda can be lambda I, where I is equal to 1, 2, 3 up to n for an n cross n matrix A, for an n cross n matrix A. Okay, so this is the for an n cross n A matrix, we will have n eigenvalues for the matrix. Okay, now how we are going to solve this? We can, if you solve this polynomial, so nth degree polynomial, we can actually find out all the eigenvalues of the matrix A. So, and the later we will see there are many methods. What are the root finding methods for even for nonlinear cases and all? You can find out how to find the root of a certain function. One can, in fact, we can use a root finding method to identify the roots, which are basically eigenvalues of this matrix A. So, and we can use it, but they are, as we see, those are not a very efficient algorithm. But on the other hand, when it's an eigenvalue problem, we are having more efficient algorithm which will enable us to find out the lambda I, that is the eigenvalue. And not only that, we may also find out what is the eigenvector corresponding to this lambda I. So those algorithms, we will see it in this series of lecture. Okay, so similarly I said, so for example, so when the lambda have n lambda values, correspondingly you will have for each eigenvector will have each eigenvalue, there will be an eigenvector associated with it. Therefore, we will have an eigenvector xi corresponding to n lambda values, and here I equal to 1, 2, 3 up to n. So this is your eigenvalue and the eigenvector. So identifying these eigenvalues and at some times even the eigenvectors is typically the eigenvalue problem, which we are going to eigenvalue problem, which will use numerical methods to find out these quantities. Fine. Now, yeah, this one thing is, sometimes if any two eigenvalues are equal, for example, some lambda I is equal to lambda j, where I is not equal to j, then you call these eigenvalues as degenerate. In general, when solving a degenerate eigenvalue problem is not very straightforward, and in this lecture we will not consider a degenerate eigenvalue problem. So we will consider the cases only when our eigenvalues are non-degenerate. That means each eigenvalue is distinct. So now, since each eigenvalue is distinct, the eigenvectors is also going to be distinct. You can't find out any, no eigenvector will be any linear combination of any other vector. So these are all linearly independent set of eigenvectors we will get. So now, since xi is a linearly independent set of eigenvectors, they can form a basis. So then any arbitrary vector x, we can write it as, for any arbitrary vector x, we can write it as an summation of these eigenvectors, and the basis of the eigenvector is a basis. That will be I equal to 1 to n, because using n cross n matrix, we will have some constant ci into xi. Okay, so, and this is the way we can actually we can use eigenvectors as a base vectors and represent any vector. Yeah, sorry, I have to write here vector. So this is a vector. Fine. So now, before we proceed into how we are numerically going to identify these vectors and eigenvectors and the eigenvalues, some interesting property of this, the eigenvalue problem is worth noting. That is, so what is eigenvalue? I removed it here. So the eigenvalue problem is matrix A dot X equal to lambda X, so on. So now suppose if I multiply both the sides by say some constant alpha. So what you are going to get, so this will be A matrix dot alpha X vector will be lambda times alpha X vector. So now we can see, so this is alpha X vector is also an eigenvector. So this is interesting. So whenever we have an eigenvector, any common multiple of that eigenvector, any constant multiple is also an eigenvector. So we won't differentiate those eigenvectors, or in fact all eigenvectors with a common factor are treated as same eigenvectors. Okay, so this will not be different. So this is the one thing we will see, and I think we can do one more part. And one more, let me add, so for instance, let me add A dot X, and I'm going to add one more term, tau X. Okay, and so here also it will be lambda X plus tau X vector. So tau is some constant, some constant value. So this I can write it as A plus tau I dot X will be equal to lambda plus tau of X vector. Now you can see. So this is also an eigenvalue problem. So what happens to the eigenvectors, the original eigenvectors, they remain unchanged. When you add up some constant term, when you add up a constant term with an eigenvalue, that's what we have done, the eigenvectors remain unchanged, only the eigenvalue change and the corresponding matrix also changes. So these two are the very important property which most of the algorithms use to find the eigenvalues and the corresponding eigenvectors. So we will be sticking to this these methods initially, and later on we will see as we go along, we will try to find out more and more important properties of this eigenvalue problem, which we can use it in our finding the numerical solution. As we mentioned, for a non-degenerate eigenvalues, so we are going to have a linearly independent eigenvector, so that can be formed as a basis of formed as a vector basis, and any arbitrary vector can be expressed in terms of those eigenvectors. So we will use this property to identify some of the eigenvalues of this matrix A. So for example, so let us have, so our matrix A, what you have considered, let it be n by n matrix. So this is going to have n eigenvalues, that is I equal to 1, 2, 3 up to n, as well as it is going to have n eigenvectors I equal to 1, 2, 3 up to n. So now, and we have all these lambda i's are distinct because you are dealing with non-degenerate eigenvalue problems. So then let me arrange these lambda i's in a descending order in the magnitude. That means what? I am going to write my lambda 1 is greater than lambda 2 will be greater than lambda 3, and it go on up to lambda n. So now, and when I arrange it, so then, and this is a general vector, so let me operate our matrix A on any arbitrary vector S. So this will be, and this I can write it as, so a arbitrary vector can be expressed in this form. So this will be matrix A, or I will take it within the summation. So what will be, so this will be summation of I equal to 1 to n C of I and A matrix operating on X of I. Okay, so this is our eigenvector. So of course this is going to be summation of I equal to 1 to n C of I, and this will be lambda I into X. This is the eigenvector I. Okay, and okay, so let me operate it once again. That means I'm going to going to multiply with the matrix A. So what I'm going to say is A matrix square into X. That is A matrix dot X. So which we have already. So when I operate it again, so what I am going to get? So this will be summation of I equal to 1 to n C of I lambda if into A operating on x of I. So this will be summation of I equal to 1 to n C of I lambda I to the power of 2, correct, into xi vector. So I can keep doing it. So for let us when I do it for say some number k times of x, so what I am going to get, so what will have the same equation but lambda I to the power of k. So we will get I equal to 1 to n C of I lambda I to the power of k of xi vector. Now from this lambda I, if I take lambda 1 commonly outside, that means what I am doing is lambda 1 to the power of k, if I take it out, so what I will get is I equal to 1 to n C of I, this will be lambda I by lambda 1 to the power of k into xi vector. Okay, so now we have assumed lambda 1 is going to be lambda larger than lambda 2. So this is going to be a means as we go lambda I movement, this will be a converging. Okay, this won't be diverging. So now, so if you see, and okay, so let me call this one as y, because this is a vector. So let me call this as y of 1, this as y of 2, and so this will be, I will call it as y of k. So now, so this one, so now as k, if you say k tends to infinity, then lambda I by lambda 1 becomes becomes 0 for I greater than 1. Okay, for I greater than 1. So eventually, because lambda 1 is larger, so if I greater than 1, this is because to the power of k. So because k tends to infinity, this goes greater than 1. So all the other terms, as the k approaches infinity, all this term vanishes. Only the term corresponding to lambda 1 remains. So this will be lambda 1 to the power of k c1 into x1 vector. Okay, so then what we have here is, what we got is a power k times x vector will be equal to c1 lambda 1 to the power of k into x1 vector, and this we write it as y of k vector. So now if you see, what's interesting is, so x1 is an eigenvector corresponding to the largest magnitude eigenvalue. Okay, so this is a vector and these are all constants. So, and y is nothing but eigenvector multiplied by a constant factor. So therefore, y is also an eigenvector. That's what we proved from there. So y is also an eigenvector, and y is an eigenvector corresponding to the largest magnitude of the eigenvalue. Okay, so this is same as your x1 vector. So, and this is the way we can find out the eigenvector corresponding to largest magnitude eigenvector value, corresponding to largest magnitude eigenvalue. Now, there's an important, so though it is very interestingly we can, so what we did is we started with an arbitrary matrix X, let us say arbitrary matrix X, and then we multiply that matrix with the arbitrary vector X, and we multiply that vector repeatedly using our matrices. What eventually will end up is that product is going to eventually lead to a eigenvalue of the matrix. Okay, and eigenvalue corresponding to the largest eigenvalue of the matrix. But yes, there is a problem. What the problem is, so if you see here, so y of k, that will be equal to c1 lambda 1 to the power of k and x1 vector. Now, if you assume the lambda 1 to be less than 1, then as k tends to infinity, so lambda 1 to the power of k becomes approximately goes to 0. On the other hand, if lambda 1 is larger than 1, so then as k tends to infinity, lambda 1 to the power of k will approaches infinity. So this is a very serious problem, because so though we are able to get this matrix Y in terms of this one, but in terms of this quantities, but this lambda 1 to the power of k, it can eventually, if a lambda 1, this can eventually make this matrix eigenvalue to be a very large number, or maybe filled with zeros or infinite big numbers, which our computer can't handle it. So therefore, what an important property we have to, important thing we have to do in this method, and that is what called as a scaling. How are we going to do the scaling? In scaling, what we do is, let us start from this equation. So what we are going to do, we are somehow wanted to avoid this lambda 1 to the power of k. So we have somehow, if you want to avoid it, then we can actually get some finite eigenvector. So in a scaling, we will achieve this. Let us see how we are going to achieve it. So let me start from this equation, that what we are having, matrix A, k dot x vector is equal to, I am going to start with this C1 lambda 1 to the power of k, and x1 vector will be equal to y vector, y of say some k vector. So how this looks like, so this is all numbers. So if you want to write it in the matrix form, how it looks like is C1 lambda 1 to the power of k. This will be a sum vector which is x, let us call x1 1, x1 2, x1 3. So let me make it slightly bigger. So what we get is, this will be C1 lambda 1 to the power of k into this vector will be x11, x12, maybe x13, you go on like that, which we write it as, say, let us call x1i. And this will be equal to, similarly, I can call this as y1, k, y2, k, go on like that. So in general, let me take some ith component from here. So when I take ith component, what this equation is going to become is, so I can remove this equation. Okay, let me write it. So the ith component will be C1 lambda 1 to the power of k into x1i will be equal to y of ith component of the kth iteration we are getting, because kth multiple times we are doing that. So now this is, let me write it here. So what we are having is C1 lambda 1 to the power of k into x1i will be equal to y of ith element of this matrix. So now if I write this one as a sum, let me call, I am going to write this as alpha times, I am taking some factor alpha times x of kth iteration. So I am going to make it as 1i, let me call. Okay, so now in the next iteration, what am I going to do? Instead of multiplying, because we have to, when I have to keep on multiplying x, basically that means I am going to keep multiplying another a with y. Instead of multiplying a with y, I am going to multiply a with xi. So that means what am I going to do? I am going to have a matrix A dot xi to the power of k. Okay, so and that is what? So this is going to be lambda 1 into xi power of k. And this will be what? It will be next iteration, correct? Because you are multiplying xi again with it. So this is going to be y of k plus 1. So sorry, I have to write here the numbers. Okay, in the component form, ith component form, what we will get is, this will be lambda 1 x of 1i of kth factor, that will be equal to y of I of k plus 1. Okay, so now suppose we have chosen this alpha such that this component becomes 1. So it means we have scaled a particular component of this eigenvector 1 as 1 by taking this common factor alpha. Then this factor is going to become 1. So what we will end up is yi of k plus 1 will be equal to lambda 1. So that means that particular component which we scaled to 1, that component will eventually become the eigenvalue. Okay, so and we can proceed further. So then what happens? So we got it. So then I can still proceed further. I am going to talk that. So yi of k plus 1, again I write it as say something like beta times x I, okay, this is x1 I to the power of k plus 1. And then again I will do the same iteration, multiply this with xi plus 1. I can keep doing it out till my, till I get this lambda 1, means I am getting more y, that every iteration this y of I becomes closer to the lambda 1. So by this we will get the lambda 1, that is the largest eigenvalue of the matrix A. And not just that, so once we get the largest eigenvalue, the y of the vector y, so that the element which we are means the element which you are scaling to 1, that will become your largest eigenvector, and this vector y of k plus 1 will be your eigenvector. This will be your eigenvalue, and this will be the eigenvector. So this particular method by which we calculate the largest eigenvalue and the corresponding eigenvector is called as your direct power method. Okay, so now, so this is, though we have got it, we need to identify how our basic concern is somehow in this jugglery, I am eliminating this lambda 1 to the power of k. I am making this k out of it so that I may get this as a finite values. So where it is happening is, to understand that, let us have a careful look at what our alpha is. So let us have a look at, I guess I can remove it. What we had is y of k will be equal to c1 lambda 1 to the power of k into x1 vector, and which we wrote it as what we wrote, alpha times, say some let me call it as x1 of kth vector. We wrote it like that. Okay, so now let me go for one more iteration. So then y of k plus 1 will be c1 times lambda 1 to the power of k plus 1 and into x1, that will be equal to lambda, so this will be 1, right? So this will be equal to, if I compare these two, what we can write, this will be lambda 1 into alpha times x1 to the power of k. So forget about c1 because that anyway will go, it's a constant, it can go into it. So when you compare these two equations, what we are seeing is alpha will be lambda 1 to the power of k approximately. We'll forget about the constant c1 because that can be taken into this matrix or whatever the form we can do. When we are normalizing, these all are taken care. So approximately your alpha, the alpha what we took out when we try to make this one, it typically goes as lambda 1 to the power of k. So by that we actually eliminated this lambda 1 to the power of k. So we are not going to multiply the lambda 1 as k infinity. That's how in this direct power method, when we do the scaling, we can eventually get an eigenvalue and the corresponding eigenvector. So this is one of a very simple and easy method to extract the maximum magnitude eigenvalue and the corresponding eigenvector. So we can just take some problem and that will give you an easy demonstration of the this direct power method. So let me do this problem. We are having the matrix A is equal to 8, minus 2, minus 2, minus 2, 4, minus 2, and minus 2, minus 2, 13. So you want to find out the maximum magnitude eigen value for this matrix and the corresponding eigenvector. How are we going to do that? So first we will start from some arbitrary matrix. Say, let us say x. So x is equal to, let us simply will take 1, 1, 1. So what are you going to do? First we are going to multiply a with x. And if I keep on multiplying a with x again and again, as the k tends to infinity, or k becomes very large, eventually that will converge to our eigenvector. Okay, and so when we do the scaling, what are the corresponding the particular component will become the eigenvalue. So we will do that here. So what you are going to do is, first one you are going to do is a dot x, that will be, so the a dot x will be, if you can multiply these two matrices, I'm straight away writing down the, so this will be the, let us say the first iteration. So that will be 4, 0 and 9. Okay, so 4, 0 and 9. So then from here I will take the one number. So let me take out the 9 commonly out. So because that's what, when the scaling what we did, we took one component and scale that component as 1. So let me pick up this component and scale it to 1. So then what I am going to become, so when I take 9 outside, so this problem, this matrix will become 4 by 9, 0 and 1. Okay, so 4 by 9, 0 and 1, or this will be equal to 9 into 0.444 recurring and 0 and 1. And then let me, now this is the matrix we are going to operate on A. Remember, that's what we did, right? We don't remove, this is the alpha we were telling earlier. Alpha, the factor we took out. So now I want to multiply this matrix again with A. So what we are going to have is, so A is what? 8 minus 2 minus 2 minus 2, 4 minus 2 minus 2 minus 2, 13 multiplied by this matrix, that is 0.444 and 0 and 1. And this will give you, I'm straight away copying it out. So if you can do it and check it, 1.555 and minus 2.88, it goes on, and 12.111, so it's a recurring. Okay, and now again here I will take out the same factor outside. So this I am going to scale it as 1, so this will become 12.111, and if I take it out, what we are going to end up is 0.128440 and minus 2.3, sorry, minus 0.238532, minus 0.238532, and then this will be 1.0, whatever it is. Okay, so then again I am going to multiply this matrix with A dot this matrix, and then again I will scale, I keep doing on. Okay, and if you remember what we did, this is our, so, and what we have done is, yeah, correct. So, I mean, this is our y of 1. This is our, if you remember, y of 1, and this will be our y of 2. And as we kept on doing out, and what is the element we are scaling? So this one. So this particular element, as we keep doing, this is the element which is going to become our lambda 1. That's the largest magnitude eigenvector, which we take it out here. So therefore this becomes a lambda 1, and this whatever left over, this becomes our eigenvector x corresponding to the lambda 1. I will call x1 vector. Fine. So we can keep on doing this again. Now if we did for y2, then you keep for y3, y4, y5, and you can keep out. And when you do the 30th iteration, what you will find is your lambda 1, that will become 13, you will see it converges, 13.870, something like that. And then you will get the eigenvectors also converges to minus 0.29. Yeah, so your eigenvector will come out to be, and that also will converges to minus 0.291 and minus 0.143435 or something, and this will be 1 because we have taken that factor outside. Okay, so this is your lambda 1 and this is your x1. So this is how we implement a direct power method to identify the largest magnitude eigenvalue and the corresponding eigenvector.